Okay, so maybe we can start. So we're very happy to have Giuseppe Scola talking about anomalous exponents and scaling operators in a fermionics side to the fourth theory. And yes, so Giuseppe, you have the stage, please.
Yes, thanks. And good morning to everyone. Thanks to be here, and thanks a lot to the organizers to give me the possibility to present my work. And today I will talk about anomalous exponent and scaling operator in fermionic 3-4D theory, dimension 1, 2, and 3. And my talk is based on a work of Giuliani, Mastropietro, and Rychkov, and a work with Giuliani, Mastropietro, and Rychkov. Indeed, the authors first construct the fixed point for this theory, and then we studied the scaling operators and anomalous exponent for the fixed point theory. Now, the plane of the talk is the following. I first give an introduction, then I present you the model and the multiscale analysis, then the fixed point theory, and I want to give an idea of the proof of the results. So let's start. Our work is in the general context of analysis of critical phenomena. So the goal at the end should be to understand scaling limit and universality, in particular for this model, but this is the general goal when we approach this kind of problem. And the road towards universality conceptually is clear. First, one can apply the Renormalization Group analysis to integrate out the small scale degree of freedom, then rescale the system and show that the critical model reaches a fixed point, where varying the scale of the system means is like changing the magnifying power of the microscope that we use to observe the system, where the system at one scale, if a similar copy of itself, up to the presence of some parameters which depend on the interaction. And then use the conformal field theory to classify the possible fixed points. So the challenge is to prove universality and conformal field theory predictions starting from an explicit microscopic Hamiltonian. So what about the conformal field theory? When we talk about conformal field theory, we have to think a collection of conformal invariant correlation function of scaling operator. So we have the operator OI with the scaling dimension delta I, and then when we do the correlation of this operator, we have that the correlation, if we apply them on x prime, is given by the correlation applied to x up to the change of variable, so that the conformal invariance fixes the 2 and the 3-point functions. And in particular, for the 2-point correlation function, if we do the correlation of OI and OIX and OJY, this goes like 1 over the distance between x and y to a power delta ij, where delta ij is the sum of the scaling dimension of the operator OI and the operator OJ, up to the fact that ij I is equal to j. So at the end, we find that this goes like 1 over the distance to 2 times delta I. And also, the conformal invariant fixes the 3-point correlation function in a similar way, up to the fact that we have some real parameters, lambda ijk. So in this context, one can express the product of two operators using the operator product expansion as the sum of the other operator up to the presence of the parameter lambda and the function fixed by conformal invariance and depending on the scaling dimension. So that solve a conformal field theory means computing the spectrum of the the scaling dimension and the structure of the constant. In such a way, we can reconstruct the correlation function. Now, this axiomatic approach does not have a relation with the macroscopic model. So what is the measure respect we do correlation, or what are the scaling operators? Otherwise, one can use the renormalization group analysis and the renormalization group fixed point theory to try to have a constructive approach to this kind of problem. For the fixed point, we know just few examples of non-trivial fixed point from constructive QFT, Lattiger liquid in dimension 2, and long-range Ising model in dimension less or equal than 3, inspired by the Wilson-Fisher fixed point for a phi4D model in dimension non-integer dimension d equal 4 minus epsilon. And an alternative to choose a non-integer d is to fix d equal 2 or 3, and then study a model with fractional kinetic term in such a way the quartic interaction will be weakly relevant in the infrared regime, which means that the RG scaling dimension of these terms will be positive and small. Now, let's see the critical behavior for the ferromagnetic long-range Ising model. So we have this Hamiltonian, and thanks to the Ginsburg-Landau formulation, we can express our action in this way, where the prediction tells us that if the S is between 0 and d over 2, we have mean field critical behavior. If S is between d over 2 and a value S star, which depends on the dimension, we have a non-Gaussian fixed point and anomalous critical exponents. And if S is bigger than this S star, we have the behavior is the same as nearest neighbor of the Ising model in dimension D. So if we fix S equal d over 2 plus epsilon with epsilon small, from the Ginsburg-Landau formulation, we have this partition function here, which is the integral respect to this measure p less or equal than 0 of e to the minus nu psi square minus lambda psi to the 4. So we have quadratic and quartic interaction. Respect to a Gaussian measure with propagator g less or equal than 0, which is given by the integration of two fields phi respect to this measure, and is given by the transform of a cutoff function k0, which is a smooth version of the indicator function that k is less or equal than 1 over k to d over 2 plus epsilon. So in this case, we can compute the non-trivial fixed point and the corresponding correlation function. Now, the case of the scalar fields phi4 in dimension 3 with weakly relevant fractional kinetic term is studied by Bridge-Smith and Scopola, but in this bosonic case, the construction of the RG fixed point result difficult for some technical reason, in particular because the terms involving fluctuation fields are on a local scale large compared with the standard deviation, so we need an a priori bound for this term. While if we consider the fermionic case, it's still non-trivial, and we don't have this problem of the large field, and we have the same qualitative properties. And then at the end, we have the same qualitative properties with less technical complication. So what we do is indeed the following. We consider a phi4D fermionic theory. And we compute the non-Gaussian fixed point effective potential, and we prove it in epsilon. This is a result of Giuliani, Mastropietro, and Rychkov. Then, in result of Giuliani, Mastropietro, Rychkov, and I, we compute the anomalous critical exponent and proving its analyticity in epsilon, and identify scaling operator for the fixed point theory associated with field and density operators. And of course, there are many things to do, for example, to prove universality, but the setting seems to be unable to study the validity of conformal field theory axioms and related issues. So let's start with the model and the multiscale analysis. So we start with the review of the work of Giuliani, Mastropietro, and Rychkov. Then we have our partition function, where with quadratic and quartic interaction respect to to a Grassmann Gaussian measure, where the fields psi are n-component Grassmann fields, and with the interaction psi square, we mean psi A, omega psi B, where omega is n times n symplectic matrix, and the quartic interaction is given by the square of the previous one, where P is again the Grassmann Gaussian integration with the propagator that we saw before. Now, here we consider interaction quadratic plus quartic term, which is the simplest interaction, but we can also add some irrelevant terms, where irrelevant means in term of the RG map, of the scaling dimension of the RG map, and then we will see soon what is the meaning of irrelevant term. We want to apply to this potential V0 the RG map, where the renormalization group map R is given by DTS, where first we do a single scale integration, then we apply the trimming operator, which is an operator which, given a term, give us the local and the interpolated part of this term, and then we apply the dilatation. So let's start with the integration. So we see how does it work, the renormalization group map. We can decompose the propagator G less or equal than 0 in two parts, G less or equal than -1 plus G0, where G0 has, instead of the cutoff function k less or equal than 0 on k, k less or equal than 0 on k minus k less or equal than 0 on gamma k, where gamma is a parameter bigger than 1. Is a fixed parameter bigger than 1. So using this decomposition, we can decompose our measure P, and then writing the field psi as psi prime plus phi, we integrate respect to the single scale 0, in this case, our potential, and in particular the field phi, so that we find an effective potential on scale -1, where the V on scale -1 is the integration of the potential on scale 0. And this is a one-step integration. This one-step integration can be done cross scale, so that we decompose in general our propagator G less or equal than 0 as the sum over H less or equal than 0 of the single scale propagator GH, where GH has this function fh of k, given by the cutoff function on gamma to the hk minus the cutoff function gamma to the minus h plus 1k. And doing a change of variable, we have that the single scale propagator GH is given by the single scale propagator scale 0 applied to gamma hx times gamma to d over 2 minus epsilon h. So we do at each step single scale integration. So that VH on scale h minus 1 is given by a single scale integration on scale h of VH. Now, having this relation between the single scale propagator on scale h and the single scale propagator on scale 0, remembering that we find this object when we integrate two fields respect to the Gaussian measure, the natural rescaling for the field psi is to choose the scaling dimension of psi as the half of this power of gamma when we pass from G to GH from G0, from GH to G0, so that the fields phi x is given by gamma h scaling dimension of psi, psi applied to the rescaled field applied to gamma hx. And this is the way that we define the dilatation operator. And then we can rescale the potential. So we start from the potential on scale A, this not calligraphical V, and we apply the dilatation on each field psi, and then we find our rescaled potential, VH, which can be written as the RG map given at this step by dilatation and integration applied to rescaled potential on scale h plus 1 is the second line of the slide, where the RG map where first we apply the integration, then we multiply with the dilatation on scale minus h and scale h plus 1, so that this gives us our RG map, which is essentially a one-step integration and a dilatation. We can read this map as a dilatation and integration on scale 0. Note that the integration are given by the identity plus the effect of the integration, so that the rescaled potential on scale h is the dilatation of the rescaled potential on scale h plus 1 plus the effect of integrations. Okay. So the rescaled potential has the following structure. So we can write it as the integral of L fields psi with a kernel WHL, where L is the number of fields psi that I have. And then we can apply our potential as a sequence of these kernels, WHL. So that the size of each kernel is measured by using this weighted L1 weighted norm. And we also have that if we consider the dilatation, okay, we have our rescaled potential V. We apply the dilatation and then we find V prime. This means that we apply the dilatation to each kernel, so that the rescaled kernel W prime is equal gamma to minus the number of fields psi times the scaling dimension of psi plus a term given by the fact that we change variable from gamma from x to gamma x, and then can you hear me?
Yeah.
And then we have that the L1 weighted norm of W prime is less or equal than gamma to P minus L scaling dimension of psi, the norm of W. Now we can define the scaling dimension of a kernel WL as the dimension minus the number of times that we have fields psi times the dimension of psi. And this object is important because I saw that before in relevant terms in RG sense, this object tell us what are the relevant or the irrelevant terms. Indeed, we say that the kernel is relevant when this quantity is positive, is irrelevant when this quantity is negative, or is marginal when this quantity is equal to zero. And in our model in particular, having that the dimension of psi is d over 4 minus epsilon over 2, the two relevant or weakly relevant terms are given by the term with L equal 2 and L equal 4. So the relevant term will be the quadratic and the kernel related to the quadratic and the quartic interaction in our case. The other one will be irrelevant. And in this sense, we can start from the beginning with the potential V0 given by quadratic, quartic, and irrelevant interaction. Then, okay, when we apply the RG map and times, we find that our system, our potential is described as a series. So we will have some divergence term and convergence term. And this will be the term, the relevant or the irrelevant terms, respectively. So we have to extract now, we have to find a way to manage the relevant terms. So we have to extract from them the local part, which is the really divergent one, and the non-local part, which will be irrelevant. This will be done using the trimming map. In such a way, the final form of the RG map will be dilatation, trimming, and then integration, which is the one that I showed you at the beginning. What is the trimming map? The trimming map is a map which is the identity on the irrelevant terms, but is given by L plus I, which is a localization plus interpolation, which are a localization and interpolation operator on the relevant terms. The localization gives us the local part of a term, which is the divergent one, and the interpolation will give us the non-local part, which will be irrelevant. So we can see how does this map works. For example, if we have the quadratic interaction. So in general, if we have a quadratic interaction, we will have a term of this type. So two fields C applied to X and Y times with the kernel W2 X minus Y. Now we want to apply, and this term here is relevant for the scaling dimension. Now we want to apply the trimming map. So we add and subtract the fields C applied to X, for example, and then we find the local part, which is nu integral of C square, plus a non-local one given by this interpolation, which corresponds to the interpolation operator applied to V2, to W2, and one derivative on fields C, where nu now is the integral of up to the presence of an omega, is the integral of the kernels W2 respect to Y thanks to the translation invariance. Now, if we check the dimension of the derivative of fields psi, this is given by gamma to minus dimension of psi minus 1. So we see that and then the dilatation of the kernel where when we apply the interpolation operator is given by gamma to d minus 2 psi minus 1. So this operator decreases by 1 the scaling dimension of W2. Then we apply again the same technique, and we find at the end that the term V2 corresponding to the non-local quadratic interaction can be written as a local term plus a non-local one where we have derivative on both the fields psi. And this is due to the fact also the local part of the one with the one derivative of the field psi is equal to 0 for symmetry reasons, so that the scaling dimension now is d over 2 plus epsilon minus 2, which is less than 0, and then we find the local relevant part and a non-local irrelevant one. And the same story, we apply the same for the case of the quartic interaction. Now, given this Banach space for the effective potential, the key point now is to control the behavior of nu and lambda under the fact that we apply the RG map R, and we have to control this behavior in order to have that the rescaled effective potential on scale h belongs to this Banach space for all h. The transformation for nu and lambda are the following. So the effective potential nu prime is given by gamma d over 2 plus epsilon nu, because the integration we saw that the integration has the identity, plus the effect of the integration, and the same for lambda, where this integration can be written as E1 times lambda for the beta function of nu plus order lambda square nu square, and D2 lambda square plus order lambda to the third lambda square nu for the beta function of lambda, where E1 and E2 can be computed explicitly, and are these two. It comes from the integration. For example, if we see the beta function of nu, we can integrate, we can have a term of type lambda, then a quartic term, and then we contract two fields of this quartic term, and we find a nu type object. And the same is
Can I ask a question? I'm getting a bit lost maybe, because on the previous slides you were talking about how it needed to be a Banach space, but I don't know what this is. Could you maybe explain what you're trying to show once more?
Sorry, I explain what is the Banach space.
So, yeah. So what are you trying to show, or why is?
So what we want is to find a way to control the evolution of nu and lambda, which will be the divergent part of the potential under the transformation of the RG map, in such a way that rescaled potential nu h belongs to the Banach space that we construct for all h. Because you see that the beta function for nu and lambda will be given by a series, so we have to control this object. I answered to your question?
Yeah, sure, yeah.
And okay, so the two beta functions are given by the series, so we have to control them. And I just say that the first term of the series related to nu and the first term of the series related to lambda can be computed explicitly and are given by these two objects.
Sorry, can I ask also another question?
Yeah.
I mean, do you have also some example? I mean, I see that you have this recipe of construction, your RG map, but can you do also some expansion with some perturbative and check with some perturbative, I don't know, some
Sure.
perturbative energy that the two things are the same. Is this different from other recipes? I don't know. Yeah. Oh.
Sorry, what do you want?
No, I don't know. Like, can you do? I mean, is this the usual RG map? I mean, can you do also some check with some perturbative approach, or is this something different and you get different numbers?
No. Okay. So the usual RG map. So you have your model. In our case, is this one, and the usual RG map is given in general by integration, this trimming operator, and then we apply the dilatation in order to rescale, okay?
Okay, already at this level, this is everything non-perturbative, right? I mean, you're not assuming any small coupling or whatever.
No, up to now, no. And this is what I have to do in order to have a fixed point to control the flux of the beta function.
Okay.
Okay? And this is indeed, I want to control the behavior of nu and lambda. So I have to fix nu and lambda, nu0 and lambda 0 properly, in such a way I can control the flux of the evolution of these two objects under the RG map. This is the point.
Okay. Okay, yeah. Okay, thanks. Yes.
Okay, then now the point is indeed to control the flow of nu, so fix nu0 up properly, and to control the flow of lambda, so fix lambda 0 properly, sufficiently small. In particular, this is the theorem of Giuliani, Mastropietro, and Rychkov. So if we fix lambda in our Banach space, we fix lambda 0 sufficiently small, and there exists, and then we have there exists an analytic function in lambda when lambda is sufficiently small, so that nu0 is this function applied to lambda 0. So that if epsilon is less or equal than this constant delta 0, which we use to define our Banach space, we have that our flux, the RG flux of the evolution of the potential under the RG map converge to a fixed point, okay? So that the kernels are analytic in epsilon. And maybe this also is an answer to the previous questions, no?
Okay.
See, yes, of course, we have to fix properly the starting point. Otherwise, this is why I told you that we have to manage the relevant kernels because this will be the divergent part of the evolution. Okay, now the question is, okay, I choose instead of the potential V0, the fixed point potential V star. And so that at scale h, I will find that VH will be equal to V star because this is the fixed point of the RG map. And then we have the fixed point theory. Now, the question is, how to construct the correlation? Are they scale and conformal invariant? What are the critical exponents and the scaling operator? And this is the second part of the work. So we will see now the fixed point theory. There are other questions about the construction of the fixed point?
So sorry, yeah, just to see if I got everything. So up to now, you've just proven the existence of the fixed point in a sense rigorously, right?
Yes, the existence of non-Gaussian fixed point for our theory.
Okay, yes, thanks.
And now we want to study a fixed point theory. So, which means that instead of choosing a potential V0, we choose V star. And then we see the correlation and related issues, okay? Okay. For the fixed point theory, we considering the following generating function, where H star now is a fixed point of this type. We have V star, which is the fixed point constructed before, and we add these two terms, phi psi and j psi square, and then we have also irrelevant terms. So, and we require that H star is a fixed point for the RG map, where the RG map is the one that we saw, up to some modification on the trimming and the dilatation due to the presence of these two external fields, phi and j. And the dilatation on the first one is that the dilatation on the fields phi give us the scaling dimension of phi, which is given by d minus psi plus an order epsilon object. And the dilatation on j, what? And the dilatation on j will give us d minus 2 times the dimension of psi plus order epsilon object, where for the fields phi, we have that this order epsilon object will be 0, while for the field j, we will have that the first order of this object is minus 2 epsilon and minus 2 over n minus 8. Now, how we construct this fixed point H star? We start from H equal to V star plus phi psi plus j psi square, and then we apply our renormalization group analysis as before, and we find that there exists a fixed point H star, which has the form that I showed you before.
Sorry, can I ask? Yeah, so you're doing epsilon expansion now? What is epsilon? Sorry, I forgot.
What is?
Epsilon? Yeah.
No, this epsilon is this one. Where is my propagator? It's the same as before. It's the one that I have in the propagator.
Okay.
Okay?
And it was what? Sorry, yeah, I forgot what it was. Yeah.
Okay. No, just to have a reminder, because our propagator is this one, no?
Mm-hmm.
Because comes from the fact that we choose S equal D over 2 plus epsilon in the action of the of the Ginsburg and Landau formulation of the Ising model.
Okay. Yes, thanks.
Okay. Okay. And of course, we saw that in the previous theorem, we saw that the parameter lambda nu, the kernels lambda nu and also the relevant kernels will be depend on epsilon because it's inside the propagator, and in particular, they are analytic in this epsilon, okay? And also this term order epsilon here in the scale dimension of J is analytic, and the first order is this one.
Sorry, the large n here is number of fermions, or what? Where does this large n?
These two fields works like fermions, but these are two artificial fields that we put inside the.
Yeah, but on the last line there's some like OJ has some expression minus 2 epsilon with some large n that appears. Last line of the slide.
This line n is chosen for sure. Here we have to choose n bigger or equal than 4, and is the number of our fermionic field. So our psi is an n. Let's go to the model for a moment.
The components of your fermion. Yeah.
You see, psi is an component from phi. Okay.
Okay. Good.
With n bigger or equal than 4. Okay. Can I go on or?
Yeah, thank you.
So, as before, we can have a representation of our fixed point in this case using the kernel representation, where now for sure the kernel W star will depend on the number of fields psi, fields phi, and fields j, and the number of derivatives that we have. So that the scaling dimension now is given by the following: d minus the number of fields phi minus the number of fields j minus the number of fields psi times the scaling dimension of each one of them minus the derivative. In particular, if we choose n equals 0, m equals 0, and p equals 0, and L equal 2 or 4, we find a quadratic and a quartic interaction. So we have to apply the trimming as before. But now, if we choose n equal 1, m equal 0, L equal 1, and p equal 0, we will find a marginal term, which is given by this one, remembering that at the end this O epsilon is 0. And also, if we choose the term with two fields psi and one field j, we find a weakly relevant term. So we have to apply the trimming also to this term. And we do as before, using localization and interpolation. Then we can associate one to the interaction phi psi and one to the interaction j psi square, so that the fixed point equation for these two objects is the following. The one on the left is on the left is the one that I have when I consider the rescaled potential, but on scale h. But now we are on the fixed point, so we don't care that this is on scale h. And the one on the right is the identity of the integration. And then in this way, we found that delta 1 is psi minus the logarithm of 1 plus zeta 1, and delta 2 is 2 psi minus the logarithm of 1 plus zeta 2, where zeta 1 and zeta 2 can be expressed as the integration. Okay. So finally, we can define our correlation. The 2-point and the density correlation, G1 and G2, given by the second derivative of W star respect to the fields phi, evaluated in phi equals 0 and evaluated in j equals 0 and then in phi equals 0. And the second derivative of V star, which is the generating function here, maybe the notation is confusing, is the generating function, not kernel, of V star evaluated in 0j respect to the fields j, and then we do the evaluation in j equals 0. For these two quantities, we have the following result. So under the same assumption of the theorem of Giuliani, Mastropietro, and Rychkov, we have that the scaling dimension of phi is d minus psi, of j is d minus 2 psi plus this object here. And if rho is gamma to the h, then G1 rho x goes like rho to the minus 2 delta 1 G1, and G2 rho x goes like rho to minus delta 2 G2, where delta 1 is the scaling dimension of psi, and delta 2 is 2 times the scaling dimension of psi plus this term eta 2. Now we can define our scaling operators, and okay, we have our fixed point h star, and let us consider the case of fields h star with fields psi, phi, and O field j. This is given by V star plus phi psi plus this term S, which depends only on fields phi, and the term R, which depends on fields phi and psi. Now, on this term R, we select all terms with one field phi and an arbitrary number of fields psi. We collect them, we put phi psi, and then this is the way that we define our operator O1. And similarly, we do for the operator O2. Then we have that the correlation function, for example, for 101 goes like G1 plus an error term which decays exponentially for x large, where now the expectation is the one with respect to the Gaussian measure e to V star psi. Okay. Now some remarks. we have that O1 and O2 are the scaling operator associated with psi and psi square, and the stretched exponential small remainder is the best that we can hope in presence of the ultraviolet cutoff. The discrete scale invariance is just technical reason, but to prove the full scale invariance, and we don't prove the full scale invariance in this work, we have to understand the invariance of the fixed point respect to gamma. Indeed, the next step of this work will be to prove the universality of the model, which means that the fixed point theory does not depend on the parameter of the RG map, which are gamma and the cutoff function key. And this is almost what we done. And if for you it's okay, I will go to some element of the proof.
Yeah.
Okay. Let's start for a simple case. We consider the non-interactive case, so the bool star equals 0. Yes, bool star equals 0. So we start from this potential bool 0, given by phi psi plus j psi square, and we have this graphical representation of these two objects. We identify the field phi with the dashed line, and the field psi with the continuous line, and the field j with this onward line. Applying the RG map, we find the fixed point potential V0 given by phi psi plus j psi square plus this term S0 and R0, where using the previous representation, S0 is given by the sum of these two objects. So in the first line, we have two fields phi and an arbitrary number of fields j, and then we contract them on scale bigger or equal than 1, because we apply n times summing over n the renormalization group map. In the second case, we only contract object of type j psi square, so that we find this kind of sum here, and then the contraction are done here. The integration are done on scale bigger or equal than 1, and the same for the term R, where we have here now a first term with one field phi and one field psi and an arbitrary number of fields j in the middle, or two fields psi. Now, what we want is to consider our generating function in this case, and our generating function is given by S0 plus the log of the integral respect to the Gaussian measure e to phi psi plus j psi square plus rho 0, so that if we apply our definition of G1 and G2, for example, for G1, we find that this is given by the propagator on scale less than 0 and the one on scale bigger than 1. So infrared plus ultraviolet regime, if you want. And we have that the first term decays as a powers of 1 over the distance, of 1 over the distance, the modulus of x to the scaling dimension of G, while the second one goes exponentially. And the same for G2. Now, if we consider a non-trivial case, so the presence of V star, the key formula is the following one. So H star is the fixed point of the RG map. So W star, the generating function, can be written as the limit as H goes to minus infinity, because it's the integration on the negative scale, of the integration and trimming applied to H star. And this is done H plus 1 times. So we multiply and dividing by d to a proper power in each every time we find t as h plus something, which means that, for example, we multiply times d to the h d minus h t integration on scale h plus 1, and then the dilatation h plus 1, the same in all of these objects. So we reconstruct the renormalization group map, and then at the end, this is the limit as h to minus infinity of the dilatation on scale h, the renormalization group map applied h modulus of h times to our fixed point, but this is the fixed point. Then at the end we have dilatation on scale h of our fixed point. Okay, in this way we have that G1 and G2 are given by the limit as h goes to minus infinity of gamma to 2h delta 1, which is the scaling dimension of this kernel, of a kernel corresponding to an object with two fields phi and no fields j or psi, and the same for G2. Of course, with gamma to 2h delta 2 and the related kernel. To prove our result, what we use is the Galavotti-Nicolò tree representation for the kernels. So let's start for the fixed point equation for our kernel. Then a kernel V star can be written as the dilatation applied to V star plus the integration. Now, if we put this term dilatation V star on the left-hand side of the equality, we will find the term of type 1 minus d, and then we divide with bar 1 minus d. We can do this because here we are considering relevant terms. So this dilatation gives us a factor, a small factor. Remembering that the map, in this case, we don't have the trimming, which is the identity on the relevant kernels. The RG map is dilatation integration. At the end, we have that our fixed point equation for the irrelevant kernels is the sum of all possible integration on the sum over k bigger or equal than 1 of the dilatation applied k time. Okay? This object can be represented using the trees, and then we can write this as sum over 3 of the value on one tree of this kernel. What does it mean? Let's see it graphically, which is maybe simple. So we identify the kernel of type nu and lambda with the big black dot, kernel of type phi associated with phi with the white square and associated with j psi square with the white rhombus. So this is a general tree, and what we do is the following. Let's start from the leaves. For example, we start from the white rhombus and the nu endpoint. This two line which goes to this small dot here means that these two terms contract in some way. And then we contract again with the other term, and we arrive to the root V0, which is our kernel. Okay. So you see that we can write when we have a line between two vertex of the tree, this means that we are doing some contraction. And then you see that we can represent our kernel as sum over this kind of tree. In particular, for the kernel with V star 2, 0, 0, 0, which means two fields phi, we have two white square and an arbitrary number of endpoints given by big dots. And then we contract them in such way at the end we find this kernel V star 2, 0, 0, 0, which correspond to the root V0 of the tree. In particular, we have that, okay, we apply we develop 1 minus d2 minus 1, the dilatation. So we have that passing from V0 to V1, V2, and V3 means that I'm doing integration between the kernel related, corresponding to V1, V2, and V3. So this can be written in terms of sub-tree, and then I do the integration of each one of this kernel, which is a sub-tree. So this is an iterative structure that can apply anytime I have a tree. And also in this way, G1 is the sum over H in Z of this object. This is allowed us to compare these two quantities. So that using the following norm, where I don't integrate respect to the variables related to fields T and J, so that if I have no fields psi, simply the absolute value, we find that the difference between gamma to 2H delta 1 W star 2000 and our G1 star goes like C over X 2 delta 1. You see, we recover here the law of the scaling operator. For zeta 1, I told you that the scaling dimension of the field phi does not have an order epsilon term, so it's given by d minus psi, because if you remember the definition of delta 1, let me check it. You see the definition here, delta 1 is given by psi minus the log of 1 plus zeta 1. If prove that this zeta 1 is 0, this is given by psi, which is what we have, indeed, because the term zeta 1 is given by this kind of term locally, which is proportional to g at 0 on scale h, which is 0 because 0 is not in the support of g at. And here, okay, here we have an example if we consider contraction between this term and a term of type 2 or lambda, but maybe I can go on. The first order computation of zeta 2, similarly, I can represent it as the sum of two tree. The first one is I have an object of type j psi square and an object of type psi to the 4. And the fact that this tree does, I start from the root and then I have immediately the white rhombus and the big dot means that I do the integration of the two fields psi square associated to j and two fields in this term lambda immediately. While in the second case, I do first the contraction of one field associated to j psi square and one field associated to lambda, and then I do another contraction in the second moment. And in terms of, in formula, this is given by the following, where using that from the fixed point equation for lambda star at the first order in epsilon is given by minus 2 epsilon log gamma over E2, where E2 is this object. Using that, this power of gamma is an order epsilon, and the fact that this integral goes like sd over 2 pi to the d log gamma, we find the fact that the first order of our object is given by minus 2 epsilon n minus 2 over n minus 8. The proof of theorem 2 is done in the same way as the proof of theorem 1, so using the tree expansion, but now using the fact that we sum over positive scale instead of all possible scale, and then we find in this way we find the exponential decay. And that's it. Maybe also I don't have time. Thank you.
Thank you. Okay, so maybe some questions. Still have some minutes of time. Maybe I can start. So in the end, your result is that you were getting the anomalous dimensions for some operators, right?
Yes, the anomalous dimension for the operator related to the density, psi square, while in this case, for the operator related to the field psi is the trivial one.
Okay, I see. And in the same way, can you also, I don't know, in the future compute maybe OP coefficients? Is that your aim, or like more proving
No,
other
yes,
things?
the general aim is now, okay, now we check the fixed point theory, and then we saw that there are something which is close to CFT, but for first we have to prove universality of our result, which means independent of the fixed point on the parameter of the G map. And then we have to check to prove the axiom of the conformal fit theorem and then the related issues for the quantity for the fixed point theory.
Okay, I see.
So in the beginning, you mentioned that you were focusing on the fermionic case because the bosonic case had some issues.
Yes.
Can you explain a bit more what these issues are, and in what where do we see that the fermionic case is easier to do?
It's easier because I'm not an expert in the bosonic case, but what I know is the following, that you define the RG map. You see that you define the RG map so that at each scale you find you define the RG map with the single scale integration, no?
Yeah.
And what I know is that in the bosonic case, when you do the single scale integration, when you divide the fields in the part that you integrate and not, you also find that the integration produces a big object big related to the scale that you are considering. So you need to an a priori bound for this object. Otherwise, you cannot control the flux of you have the mass essentially. Otherwise, you cannot control the flux of the RG map. And then we have to estimate this object, this part with other bounds using, for example, cluster expansion, if I remember well. While in this case you don't have, because you divide exactly your fields in the part that you integrate out and the one that you have on the other scale.
Okay, I see. And then another, like going further into the comparison with the bosonic long-range Ising, there you have some operators that have protected dimensions. Like in the bosonic case, it's phi and some phi cubes in this expansion. Do you have something similar here? Because the two scaling operators you find are not psi, as you said, right? So is there some psi and some other operator that are protected? Or?
No, the general, no, so you see, we define our function G1, which is related to psi, okay? Correlation psi in this way, and the function G2, which is related to the correlation psi square in this way. But what we found is that if we have a more general operator given by psi to the third, psi to the 5, or psi square plus psi to the 4, and so on, which are scaling operator associated with psi square, because the main part, the element part, will be given by psi square in both. Psi in one and psi square in the other. You have that you express them using this GI, which are exactly psi and psi square. Okay, just the last line. I have some bibliography about the things that I told at the beginning.
Okay, are there any other questions? So, if not, let's thank Giuseppe again.
Thank you. I hope it was interesting.
Thanks, Giuseppe, and okay, we'll see you in 5 minutes. Thank you.
Okay, see you. Thanks.